Hello, everybody. Before starting the talk, I would like to thank the organizers of this geometric analysis past, present, and future activity, and especially the organizers of the constant mean curvature session. So I'm going to share my first slide with the title of the talk. It is elliptic Weingarten surfaces. And especially we are going to deal with the classification of entire graphs and complete multigraphs, which is related with the Bernstein problem. This is a joint work with José Antonio Gálvez from the University of Granada and Pablo Mira from the University of Cartagena. So I've divided the talk in several parts. In this first part, I'm going to make an introduction to the theory of elliptic Weingarten surfaces and why they are related with CMC surfaces. And I'm going to also state the problems that we are going to address in the talk. So, well, for any surface in R3, oriented surface in R3, if we have the two principal curvatures, K1 and K2, the curvature diagram is the set of the plane where the principal curvatures live. So if we assume that K1 is the greatest principal curvature, then in general, the curvature diagram is going to be some two-dimensional region in the half plane determined by the diagonal K1 equals K2. Well, in this setting, Weingarten surface is nothing but a surface for which the curvature diagram is actually a curve. So you have some equation that relates the two principal curvatures. And I'm going to assume that this relation is symmetric in K1 and K2, so that my Weingarten equation can be rewritten in terms of the mean curvature and the Gaussian curvature. So this notion of Weingarten surface is classical. It appears in the works by Hoff and Chern and many others. And among all the Weingarten surfaces, there is a special type, and they are called elliptic Weingarten surfaces. And these are the surfaces for which the function W that defines the equation between the two principal curvatures satisfies this other condition, which is nothing but the ellipticity condition for the elliptic partial differential equation that we get when we write the equation in terms of, so if we have a surface and locally around a point, we express the surface as the graph of a function over the tangent plane, then the Weingarten equation transforms into a second order partial differential equation for the function defining the graph. So this condition for elliptic Weingarten surfaces is nothing but the ellipticity condition for this underlying partial differential equation. So in this sense, this reminds what happens in CMC surfaces and minimal surfaces, because constant CMC, constant mean curvature surfaces are known to have an underlying quasi-linear elliptic partial differential equation. While in this more general setting of elliptic Weingarten surfaces, what we have is an underlying fully nonlinear, in general, elliptic partial differential equation. So in some sense, elliptic Weingarten surfaces represent a natural extension of the theory of constant mean curvature, including minimal surfaces. Regarding this equation of elliptic Weingarten surfaces, for our purposes in this talk, it's going to be more convenient to rewrite this equation in the following way. This condition here is equivalent of saying that on each connected component of the points where W is equal to 0, each connected component is actually a curve in which we can write one principal curvature as a decreasing, strictly decreasing function of the other principal curvature. So this is how we are going to write the condition of being elliptic Weingarten a surface. And once we have this condition, it exists a unique point in which this curve, that is the curvature diagram of our surface, is going to meet the diagonal. K1 equals to K2. This corresponds to the umbilical points. So if, and this number that is going to denote by alpha, and it's called the umbilical constant, this is the value of the principal curvatures at the umbilical points of our surface, and it's always the same value. And if this value is equal to 0, we are going to say that the surfaces are of minimal type. And if this value is different from 0, as it happens in the example that is pictured here, we are going to say that the Weingarten surface is of non-minimal type. An interesting feature is that in the minimal type elliptic Weingarten surfaces, we always have planes. Planes belong to the family. And in the non-minimal case, we always have spheres of a suitable radius belonging to our family of elliptic Weingarten surfaces. So regarding examples, of course, we have the easy ones that are the constant mean curvature surfaces and minimal surfaces. In this case, the curvature diagram is a line of a slope -1 starting from the origin in the case of 0 mean curvature, and starting from a different point in the case of non-zero constant mean curvature surface. Have the classical examples of positive constant Gaussian curvature. Positive is in order to have the ellipticity condition. In this case, the curvature diagram is a curve like this blue one in the picture, which is asymptotic to the K1 axis. And there is also a well-known type of elliptic Weingarten surfaces known as elliptic linear Weingarten surfaces. In the linear equation is in terms of the mean curvature and the Gaussian curvature. And this condition between A, B, and C is in order to have the ellipticity condition. In this case, the curvature diagram is a curve asymptotic to a horizontal line. And well, these are, let's say, the most well-known and studied examples of elliptic Weingarten surfaces, but there are also general examples and results regarding these families. So, for example, in 1999, Saer Pantuviana classified all the complete rotational elliptic Weingarten surfaces. So for a given Weingarten equation, they classify all the possible rotational examples that satisfy this Weingarten equation. And it turned out that the situation is quite similar of the situation of constant mean curvature surfaces. So we have spheres, as I said before. We have some onduloid type surfaces. We have cylinders, and we have some nodoid type surfaces. This is for the non-minimal case. In the minimal case, we have catenoidal type surfaces. And a nice different situation here, when we compare with the setting of minimal surfaces, is that minimal type elliptic Weingarten surfaces, in the rotational case, these catenoidal type surfaces can or cannot have bounded height. So the catenoid in R3 is always unbounded, but elliptic Weingarten surfaces of catenoidal type can have bounded height. It depends on the behavior of the function defining the Weierstrass, the Weingarten relation. So this is the classification of complete rotational surfaces. For CMC and minimal surfaces, actually any rotational surface must be a part of a complete one. So this is actually all the examples, but different thing that happens here is that this is not the case for general elliptic Weingarten surfaces. So not any rotational surface must be part of a complete example because singularities can appear. And in a recent paper with Pablo Mira, we classified all rotational elliptic Weingarten surfaces. If they don't have singularities, then they are part of Saer-Pantuviana examples. But if they have singularities, then we have some other examples that you have here that are kind of the singular versions of the examples above. So we can have either isolated singularities or a curve of singularities at the boundary. Well, we have also some global results known for elliptic Weingarten surfaces. We have an Alexandrov type theorem, and the proof is actually the same as in the constant mean curvature case because the main tool used here is the maximum principle for elliptic partial differential equations. So we also have a maximum principle for elliptic Weingarten surfaces because they also satisfy an elliptic partial differential equation. So the theorem here says the same as the classical Alexandrov theorem for constant mean curvature surfaces. Any compact embedded elliptic Weingarten surface has to be a round sphere. We also have a Hopf type theorem that classifies all the genus zero compact surfaces. So if your surface is topologically a sphere, then it has to be a round sphere. And in this case, the proof is not so straightforward, and it was done by Hopf, Chern, and Harman and Winter with the less regularity conditions for the function defined in the Weierstrass relation. And also we have some similar theories similar to what happens in the constant mean curvature case when studying the properly embedded ends of surfaces in the non-minimal type, and the finite total curvature theory for surfaces of minimal type. So in some sense, as I have said before, elliptic Weingarten surfaces are a natural extension of the theory of constant mean curvature surfaces, in the sense that we have a curvature condition that has an underlying elliptic partial differential equation that is not quasi-linear anymore. It is fully nonlinear, but still has some similarities. So a natural object, a natural aim in this field is to try to extend the results that are known for constant mean curvature surfaces and minimal surfaces. So the one I'm going to focus in this talk is the classical Bernstein theorem in R3. The classical Bernstein theorem says that any entire graph with constant mean curvature has to be a plane. There are no other examples of entire graphs with constant mean curvature. Actually, for non-zero constant mean curvature, the problem is trivial, so it only makes sense in the case of minimal surfaces. It's the only case in which it's not trivial. The proof in the non-minimal case goes as follows. It's just an application of the maximum principle. Because if you have an entire graph of non-zero constant mean curvature, this is the green surface here in the picture, we can always take a sphere with the same mean curvature and place the sphere up enough if we have oriented the surface with upwards normal, for example. We place the sphere up enough so that at the beginning it doesn't intersect your graph, and then you start moving down the sphere until you get to a first contact point. In this point, you have a surface that is two surfaces that are tangent, and one of them is above the other. And this contradicts the classical maximum principle for elliptic partial differential equations. So it's impossible. The only possibility is that both surfaces are actually the same, but one of them is a sphere and the other one is an entire graph, so they cannot be the same. So Bernstein theorem can be stated only in the case of minimal surfaces, is where it actually makes sense. So a natural problem in our setting is to try to extend this result for entire graphs of elliptic Weingarten type. This was posed by Rosenberg-Saerp in a paper in '94 for Weingarten surfaces. And as it happens in constant mean curvature, in the non-minimal case, the problem is trivial, and the same proof holds because we have maximum principle and we always have spheres for a certain elliptic Weingarten family. So this is one of the problems that we are going to address in this talk. And the other one can be seen as some kind of generalized Bernstein problem. So let me first make some observations. So first one is that if you have a graph, entire or not, the Gauss map, the unit normal vector, always takes values on an open hemisphere, always points up or down. But the converse is not always true. So a surface is called a multigraph or a local graph if the Gauss map takes values on an open hemisphere. So multigraphs are surfaces that are locally a graph. So the vertical projection on the horizontal plane is a local diffeomorphism, but not a global diffeomorphism. Okay, so these are multigraphs. And so this result by Hoffman and Osserman and Schoen in the 80s can be seen as some kind of generalized Bernstein theorem. Instead of working with entire graphs, we deal with complete multigraphs. It's some weaker condition. And the result is the same. The only possibilities are the planes. Here, the non-zero mean curvature case is not trivial. So here is the mean curvature, the non-zero mean curvature is actually a non-trivial situation. And so it leads us to this new problem. This is what we have called the generalized Bernstein problem that was proposed by Saerp and Tubiana in a paper in 1999. So is this theorem still true? So is planes the only elliptic Weingarten complete multigraphs? So this is going to be the aim of the talk. We are going to, well, to see some previous approaches and partial solutions to this problem, and then I will explain our contribution to them. But this will be in the next part of the talk.